Hello and welcome to the fifth lecture in Mandate 1 for the course on Artificial General Intelligence, topics in Artificial General Intelligence. So far, we have seen a brief history of AI and the way it has developed over the years and the different AI winters that it went through, right? And so each new wave of AI was characterized by some kind of an inflection point. For example, the initial years were characterized by advances in formal logic and symbolic reasoning and so on. And later on, we had more different waves, which in turn were characterized by, say, advances in neural networks, advances in robotics, embedded robotics, autonomous agents, and so on, right? And so each of the different waves that we have seen for AI has had its own unique signature, right? In this lecture, what we'll see is let us again take a step back and try and address the problem of what is meant by intelligence in the first place, right? And especially if we are talking about artificial intelligence, we not only need to specify or define intelligence, we need to also be able to define it in a way that it can be mechanized into a machine, right? We can build machines, artificial machines, out of such a definition. So in this lecture and the next, let us look at the different models of artificial intelligence that have emerged, and let us see, let us compare and contrast each one of them and see where each one of them are applicable. What are the implications of each one of them? Okay. So let me start by sharing my screen. Yeah. So let's start with different models of AI. And so we'll start by first observing that artificial intelligence, or AI, suddenly has to address a lot of questions that were hitherto in the realm of philosophy, right? So when we are asking what is meant by intelligence, along with it, we are actually asking a lot of things, right? We're asking things like what is meant by consciousness or sentience, knowledge, epistemology, semantics, free will, right? So what is meant by autonomy, free will, embodiment, cognition, ethics, a lot of these things that were hitherto in the realm of philosophy now suddenly has become mainstream. And we as engineers or scientists need to address this. And even as we speak, there are technological innovations that are pushing the boundaries of what we kind of understood as the definitions of each of these topics, right? And so there are several schools of thought, philosophical schools of thought when it comes to AI, and we'll see some of these as shown in this in the list on your side. So we look at AI as so this was one of the first definition towards intelligence, as intelligence is observable behavior. Or intelligence as a simulation of reality and so on, and intelligence as a formal symbol manipulation mechanism, intelligence as embodied cognition, and intelligence as agency. Next, after this, we'll also look at what we call hermeneutics of intelligence. Hermeneutics broadly means the way of thinking, the underlying, foundational elements of how we approach, a thought process, right? A line of inquiries. So we look at things like strong and weak camps in AI, and neats and scruffy camps, and so on. And we'll also look at some models of AI ethics. What are all the hermeneutics of AI ethics, and so on. Later on, of course, we have a complete mandate on AI ethics, but here we'll just look at this in the context of how to define what is meant by intelligence. Okay, so let us start with the first definition of intelligence. I'm sure you must have heard of the famous Turing test. So this was one of the thought experiments proposed by Alan Turing in his paper entitled "Can Machines Think?" Okay. So in this Turing test, the idea was that we can presume that a machine is able to think if another thinking being, right, like for example, a human being, okay, is unable to distinguish between a machine and a human after significantly long series of interactions. Okay, so imagine that there is a there are two windows here. Okay, so behind the window, behind one of them is a machine, a computer. Okay, and behind another is a human being, right? And there's a human being here which who is interacting with both of them, carrying out a conversation with both of them. And let us say the human is unable to say which is a machine and which is a human, then we can safely conclude that machines can think. So it's a kind of a circular definition, if you ask me, that we kind of define thinking in terms of what another thinking agent can, would say about this. So there's a related concept of this, which is also called duck typing. Okay. So which nowadays it's used in programming as well. In a lot of programming languages, where if you want to understand the type of a variable, you just look at the context in which it is used, and then you can, it will automatically infer the type of variable. Okay, so colloquially, it can be thought of as this. If something looks like a duck and quacks like a duck and waddles like a duck, it's probably a duck. Right? And the idea of duck typing has also been used in a lot of political debates as well. So famously, in a debate between in a US debate, one of one of the debaters said to the other, called the other a communist, and the other said, no, I'm not a communist. So then it gives something like this, saying that if someone acts like a communist, argues like a communist, and works towards pushes, advocates policies of communism, then is probably a communist. Okay, so that's the idea behind this. It's also sometimes called the polite convention approach. So polite convention basically means that we are not really debating the fundamental question, okay, as to what is intelligence, or what or whether we are intelligent in the first place, right? So here we're using a human being as the arbiter of whether something is intelligent. So there is there's an underlying assumption that the human being is intelligent, right? And the human being kind of represents the benchmark for intelligence, and we are comparing against this benchmark, right? So if it's assumed that a given human being can think, then any computer that can mimic the human being can also be termed as thinking. Yeah. So of course, this definition of intelligence is not without its criticism and detractors. There are quite a few detractors to this. So one of the well-known one is the Searle's John Searle's Chinese room argument, right? I'm sure you must have heard of it in one of your courses on AI and so on. So what is the Chinese room argument here? So imagine that there's a person, a clerk, let us say, who does not speak any Chinese, okay, but he's made to work in a office where all transactions are in Chinese, right? And so he's given a table where he'll get some requests written in Chinese, and he has a huge rule book saying that if the request looks like this, you need to do this, and if the request looks like this, you need to do this, and so on, right? So he's given a big rule book. So it basically matches the pattern, okay, the pattern of the request and the pattern of the rule, and then follows the rules. Okay? So to someone interacting with the clerk, it appears that the clerk is able to understand Chinese, right? The clerk is able to kind of is able to understand what's going on, but actually what the clerk is doing is blindly following some rules without actually understanding the semantics of what it's doing, right? What he's doing. So that's the same thing here with the computer, that you can actually build chatbots today. For example, today we can actually build a lot of conversational AI and chatbots, which do carry out a conversation pretty, in a pretty believable fashion, right? And but do they really understand what is going on? Right, so conversation is still considered different from natural language understanding. So right, and so for example, can they kind of exploit the conversation to their own benefit or to the benefit of whoever has written for them? So, right, and are they intelligent enough? So that's one. That's one of the detractors against observable behavior. Just because something appears observably intelligent may not necessarily mean that it is intelligent. Similarly, Peter Wagner, in around the year 1997, he wrote a very interesting paper called "Why Interaction is More Powerful Than Algorithms." This was in CSEM, Communications of the ACM paper, where he basically, the argument he makes is that if any machine or an agent, okay, rather than doing its own thinking, if it just reflects the complexity that is there in its environment, okay, then it can actually appear to be intelligent without necessarily being intelligent itself, right? And so what was Wagner's answer to the Turing test? So Wagner's answer to the Turing test is that, so let us say I build a machine, okay, which can pass the Turing test in a very simple fashion. Okay, what is the simple fashion I can build? Let us say behind two windows, here there's a human, and here there's a machine. Okay, but the machine has a back door. Okay, so here the machine has some kind of a back door through which it in turn interacts with another human behind it, right? So whatever question this human poses, all that the machine does is it gives it to the human through the back door and gets the answer and answers it back here, right? And so now you see the machine is actually in some sense doing something intelligent, right? That is, instead of trying to answer the problem myself, I'm delegating it to another human who I know can answer these questions, right? And then I'm answering it on behalf of the human. So you see that, so whether can you call this kind of machines as intelligent, right? And so that's one of the detractors in the sense, I mean, there's much more to observable behavior, because you can produce observable behavior in many different ways without necessarily being intelligent and so on. Then there is, of course, another detraction statement from Russell and Norwick, who are known for their well-known book on artificial intelligence. So they start by asking whether observation itself is a suitable goal for for achieving something, right? And so so basically what they say is that suppose aviation engineers, aeronautical engineers, if they started thinking like this, then for them a flying machine would be something that it's a machine that say that looks like a pigeon and acts like a pigeon and fools real pigeons into thinking that it's a pigeon, right? And so do we actually need that? Do we actually need a computer to fool a real human being into thinking that it's a human being to be termed intelligent, right? And in fact, we can actually achieve our goals of intelligence without actually needing to get into a conversation with a human being. Okay. So which also comes to the criticism here. It's that the idea of observable behavior or the Turing test kind of approach to intelligence is overtly anthropomorphic, right? It makes sense only in a human conversational setting, right? And for example, we know that a fish is quite intelligent in itself, right? And it can fend for itself, it can hunt for food, it can escape from predators, it can reproduce, it can it can coordinate with other fish and so on, right? So it can do a lot of intelligent behavior, right? But it still cannot carry out a conversation with a human and fool a human into thinking that it's human, right? And so there are elements of intelligence which need not necessarily come to anthropomorphic tests like the Turing test. So that's about that's a very brief or quick overview on the first model of intelligence that that we saw as intelligence as as observable behaviors. So let us now look at the next model of intelligence, namely intelligence assimilation. Right? So the way to understand this is that we can imagine ourselves to be intelligent because we have a simulation of reality inside our minds, right? So there is a mental universe and there's a real universe, right? And we are able to simulate what happens. So we are able to build a model of reality inside our heads and simulate what might happen and how things are affecting one another and so on. And that's what makes us intelligent. Okay. So that's the so suppose we can do the same thing for AI, right? Suppose AI can simulate our brains. Okay. Now, can that be called intelligent, or can it become intelligent? Okay. So by simulating reality, we are becoming intelligent, and by simulating our brains, can we create an artificially intelligent machine? Okay. So this is the line of approach that that is taken in intelligence assimilation, right? So Hubert Dreyfus, for example, has made a very characteristic statement in this regard that if our nervous system obeys the laws of physics and chemistry, right, we should be able to reproduce the behavior of the nervous system with some physical means, right? And so can we kind of simulate the brain and then do whatever the brain does, and then it becomes intelligent, right? And so this is based on the argument that it's just computing power that holds us back from manifesting true intelligence in machines. Okay. So there are quite a few projects or efforts in this area about brain simulation, or also what is called artificial mind. So there are some approaches which take direct brain emulation using neural networks, artificial neural networks, and high performance computing and so on. Then there are approaches that take evolutionary algorithms to evolve neural connections, like somewhat like what the brain does and so on. And there are architectures which don't take a neural network model, but then take a cognitive architecture. For example, there's so many cognitive models of the brain, like say the working memory, then episodic memory, semantic memory, procedural memory, and the way they all interact and so on, right? And so can we combine all of these together and then get something of an artificial brain and so on? Okay. So this is also called brain emulation or cognitive neuroscience. Of course, there are detractors to this in the sense of which is for example, the Chinese room argument. Basically talks about how if we are actually computing something, are we really understanding this and so on? But the argument here basically says yes, in the sense that computing equal to understanding, right? And that is, if you are able to do everything that the brain does, right? Then the fact that we are computing, we are also understanding, or we are doing whatever the brain is doing, right? And but this also brings in other questions. One of the more fundamental questions is whether intelligence is computable, right? So computable, I'm using the term computable as in the theory of computation, computable functions. So whether so you must have taken up some course in discrete mathematics and computation, theory of computation and so on, where you would have learned that not every mathematical function is actually computable. Right? There are actually some mathematical functions for which, even in theory, we cannot build an algorithm. Right? And there's something called as the halting problem, then post correspondence problems, and quite a few such approaches. Predicate logic entailment problem, the generalized entailment problem, and so on. Each of which are known to be uncomputable. We cannot, even in theory, build an algorithm that will give us an answer for all possible cases of these problems. Okay? But brain emulation basically is saying that intelligence is computable, right? I mean, all that the brain does is to compute computable functions. Okay. Of course, there's a major detractor to this, Roger Penrose. He has written a well-known book called The Emperor's New Mind, where he argues that intelligence is not computable. That is, what we do in our brain cannot be represented using an algorithm or a Turing machine. And every computer, as you know, is a Turing machine, right? And at the core, right? And so, but of course, that's an open question in the sense that we don't have any proof for whether intelligence is either computable or not. Penrose goes on to write another book. It's called Shadows of the Mind, where he basically argues that what we call as mind and consciousness has to do with quantum effects, which cannot be manifested in present-day computing, at least. But there are authors like Ray Kurzweil, who has written a book called The Singularity is Near, where he argues that it is in fact possible that computers can emulate an entire brain, right? And so not just simulate it, can even emulate the entire brains. So that's a quick overview of intelligence simulation. And of course, other detractors for this is again the Norwich's pigeon argument. That is, should we have in order to build something intelligent, okay, and we know that the source of intelligence in nature is our brain, okay, do we have to actually emulate the brain, right? So if in order to build a flying machine and we see that a pigeon is a flying machine, do we actually have to emulate the entirety of a pigeon, right? And so that's the question, that we may not really need to emulate an entire brain in order to build something intelligent, or even generalized intelligence, and so on, right? And it may be possible to understand and represent intelligence without mimicking the complete extrinsic form, right? The complete brain. And of course, once we create a brain, probably we have to test it only using the polite convention method, right? And by observable characteristics method. Okay, so basically we covered two models of intelligence in this lecture. One is intelligence as observable behavior, which dates back to the Turing test. Then we saw what are all the philosophical underpinnings behind intelligence as observable behavior, the criticisms or detractors for that. Then we saw intelligence as simulation. And by simulation of the brain, can we build artificially intelligent machines, which is of course taken very seriously, and there's so many different labs which are working on that. And although while the quest itself could be somewhat pointless, like say what Norwich would talk about, right? And just the fact that we are putting so much effort into understanding how the brain works and emulate it, okay, can give us a lot of insight into building, making progress in AI in so many different ways, right? And it also gives us a lot of understanding into our own mind itself, the way the brain works and the way the mind manifests within our brain. So, so with this, let me stop at this note for this lecture. In the next lecture, I will take on a few more models of intelligence, and we'll again study the what does this perspective tell us about what is meant by intelligence. Thank you, and see you in the next lecture.